it is permissible to use a number 10 neutral conductor for an air handling unit protected by a 35 amp 3-pole breaker given certain conditions. These conditions primarily relate to ampacity requirements as dictated by the National Electrical Code, or NEC. Firstly, the phase conductors feeding the air handling unit must be number 8. Secondly, the minimum circuit ampacity for the air handling unit must be 27.3 amps. Thirdly, the maximum overcurrent protection device, often referred to as the OCPT, must not exceed 40 amps. The critical consideration here is the ampacity of the neutral conductor relative to the maximum unbalanced phase current. According to the NEC, the neutral conductor's ampacity must be no less than the maximum unbalanced phase current. In simpler terms, the neutral wire must be able to safely carry the maximum current it is expected to handle under normal operating conditions. To determine if a number 10 neutral is suitable, we need to compare its ampacity with the calculated maximum unbalanced phase current. A number 10 copper conductor, in typical installations, has an ampacity of 30 amps according to NEC Table 310.15b16, assuming it is rated for 75 degrees Celsius and installed in a typical raceway or cable assembly with no more than 3 current-carrying conductors. The maximum unbalanced phase current in this scenario is 27.3 amps, which is the minimum circuit ampacity for the air handling unit. Since 27.3 amps is less than the 30 amp ampacity of the number 10 neutral conductor, it appears to be compliant with the NEC. However, it is crucial to consider several other factors before making a final determination. These factors include the type of load, the presence of any significant harmonic currents, and any applicable directing factors for ambient temperature or the number of conductors in a raceway. Firstly, let's consider the type of load. Air handling units typically consist of motors for fans and compressors, as well as resistive heating elements in some cases. Motors can introduce harmonic currents into the electrical system, particularly odd-order harmonics such as the 3rd, 5th, and 7th harmonics. These harmonic currents can increase the current flowing in the neutral conductor, even in a balanced three-phase system. If the air handling unit is known to produce significant harmonic currents, it may be necessary to increase the size of the neutral conductor to accommodate the additional current. The NEC addresses harmonic currents in section 220.20, which requires the neutral conductor to be sized to carry the maximum neutral current, including any harmonic currents. Secondly, we must consider any applicable directing factors. If the conductors are installed in an environment with a high ambient temperature, the ampacity of the conductors must be derated according to NEC Table 310.15b. Similarly, if there are more than 3 current-carrying conductors in a raceway or cable, the ampacity of the conductors must be derated according to NEC Table 310.15 cone. These derating factors reduce the allowable ampacity of the conductors, and it may be necessary to increase the size of the neutral conductor to compensate for the derating. For example, if the ambient temperature is 40 degrees Celsius and there are 4 current-carrying conductors in a raceway, the ampacity of the number 10 neutral conductor may need to be derated to 80% of its original value, which would reduce its ampacity to 24 amps. In this case, a number 10 neutral conductor would no longer be sufficient, and a larger conductor would be required. Another critical aspect to consider is the voltage drop in the conductors. The NEC recommends limiting the voltage drop to no more than 3% for branch circuits and 5% for feeders. Excessive voltage drop can cause equipment to malfunction and can also reduce the efficiency of the electrical system. The voltage drop in a conductor is proportional to the length of the conductor and the amount of current flowing through it. If the air handling unit is located a significant distance from the electrical panel, it may be necessary to increase the size of the conductors to reduce the voltage drop. To calculate the voltage drop, you can use the following formula: voltage drop equals 2 times K times I times D divided by circular mils, where K is the constant for the conductor material, which is 12.9 ohms circular mils per foot for copper. I is the current in amps, D is the one-way distance in feet, and circular mils is the circular mil area of the conductor. For a number 8 copper conductor, The circular mil area is 16,510 circular mils, and for a number 10 copper conductor, the circular mil area is 10,380 circular mils. If the calculated voltage drop exceeds the recommended limits, you must increase the size of the conductors until the voltage drop is within acceptable limits. Furthermore, the type of wiring method used can also affect the allowable ampacity of the conductors. The NEC specifies different ampacity ratings for different wiring methods such as THHN, THWN, and XHHW. It is important to select a wiring method that is suitable for the environment in which the conductors will be installed and to use the appropriate ampacity rating for that wiring method. For example, THHN conductors have a higher ampacity rating than THWN conductors, but THHN conductors are not suitable for wet locations. Therefore, if the conductors will be installed in a wet location, you must choose THWN conductors and use the lower ampacity rating. In addition to the NEC requirements, it is also important to consider any local codes or regulations that may apply. Local codes may have more stringent requirements than the NEC, and it is important to comply with all applicable codes. For example, some local codes may require the use of a larger neutral conductor than what is required by the NEC. It is also important to ensure that the electrical installation is performed by a qualified electrician who is familiar with the NEC and local codes. A qualified electrician will be able to properly size the conductors, install the wiring, and ensure that the installation is safe and compliant with all applicable codes. In summary, while a number 10 neutral conductor may be permissible for an air handling unit with a 35 amp breaker under specific conditions, it is essential to carefully consider all relevant factors, including the type of load, the presence of harmonic currents, derivative factors, voltage drop, wiring method, and local codes. Consulting with a qualified electrician is highly recommended to ensure a safe and compliant installation. The NEC also provides specific guidelines for sizing neutral conductors in various applications. For example, Section 220.61 covers the sizing of neutral conductors for household ranges and cooking appliances. This section allows for a demand factor of 70% to be applied to the neutral conductor size, provided that certain conditions are met. However, this demand factor does not apply to air handling units, as they are not considered household ranges or cooking appliances. Another relevant section of the NEC is Section 310.15, which provides the allowable ampacities of insulated conductors. This section includes tables that list the ampacities of various conductor sizes and types, based on the insulation temperature rating and the number of current carrying conductors in a raceway or cable. It is important to use these tables to determine the appropriate ampacity rating for the conductors being used in the installation. In addition to the NEC, there are also various industry standards and guidelines that provide recommendations for electrical installations. For example, the National Electrical Manufacturers Association, or NEMA, publishes standards for electrical enclosures, wiring devices, and other electrical equipment. These standards can provide valuable information for selecting and installing electrical equipment. It is also important to consider the long-term reliability and maintainability of the electrical installation. Using high-quality materials and proper installation techniques can help to ensure that the installation will provide reliable service for many years to come. Regular maintenance, such as inspecting and tightening connections, can also help to prevent problems and extend the life of the installation. Furthermore, it is important to document the electrical installation properly. This documentation should include a wiring diagram, a list of materials used, and any calculations performed to determine the conductor sizes and overcurrent protection. This documentation can be valuable for troubleshooting problems and making future modifications to the installation. In conclusion, determining the appropriate size of the neutral conductor for an air handling unit with a 35 amp breaker requires careful consideration of various factors, including the NEC requirements, local codes, industry standards, and the specific characteristics of the load. While a number 10 neutral conductor may be permissible in some cases, it is essential to verify that it is sufficient to carry the maximum unbalanced phase current, taking into account any harmonic currents, dirting factors, voltage drop, and other relevant considerations. Consulting with a qualified electrician is highly recommended to ensure a safe, reliable, and compliant electrical installation. Remember, electrical safety is paramount, and it is always best to err on the side of caution when designing and installing electrical systems. Improperly sized conductors can overheat, causing insulation damage, fires, and other hazards. By following the NEC and other relevant guidelines, and by working with a qualified electrician, you can help to ensure that your electrical installation is safe and reliable. Let's delve a little deeper into the concept of unbalanced loads and how they affect the neutral conductor. In a perfectly balanced three-phase system, the current in each of the three-phase conductors is equal in magnitude and 120 degrees apart in phase. In this ideal scenario, the neutral conductor would carry no current at all. However, in reality, electrical loads are rarely perfectly balanced. This means that the current in each of the three-phase conductors is not exactly equal, resulting in a current flow in the neutral conductor. The magnitude of the current in the neutral conductor depends on the degree of unbalance in the load. The greater the unbalance, the higher the current in the neutral conductor. To calculate the maximum unbalanced phase current, you need to determine the maximum difference in current between any two of the three-phase conductors. For example, if the currents in the three-phase conductors are 25 amps, 27 amps, and 28 amps respectively, the maximum unbalanced phase current would be 3 amps, which is the difference between 28 amps and 25 amps. In the case of the air handling unit, the minimum circuit ampacity of 27.3 amps represents the maximum current that the unit is expected to draw under normal operating conditions. This value can be used as a conservative estimate of the maximum unbalanced phase current. However, it is important to note that the actual unbalanced phase current may be higher if the unit is subjected to abnormal operating conditions such as a motor starting or compressor cycling. Therefore, it is always best to err on the side of caution and use a larger neutral conductor than what is strictly required by the NEC. Let's also discuss the importance of grounding in electrical systems. Grounding provides a low impedance path for fault currents to flow back to the source, which helps to trip the overcurrent protection device and energize the circuit in the event of a ground fault. The grounding conductor is typically a green or bare wire that is connected to the equipment grounding terminals of electrical equipment and to the grounding electrode system at the service entrance. The size of the grounding conductor is determined by the size of the overcurrent protection device protecting the circuit. The NEC specifies the minimum size of grounding conductors in Table 250.122. It is important to use the correct size grounding conductor to ensure that the fault current can flow back to the source quickly and safely. In addition to the equipment grounding conductor, there is also the neutral grounding conductor, which is connected to the neutral point of the electrical system and to the grounding electrode system at the service entrance. The neutral grounding conductor provides a reference point for the voltage in the electrical system and helps to stabilize the voltage under unbalanced load conditions. The size of the neutral grounding conductor is determined by the size of the service entrance conductors. The NEC specifies the minimum size of neutral grounding conductors in Table 250.66. It is important to use the correct size neutral grounding conductor to ensure that the voltage in the electrical system remains stable and that the system operates safely. In conclusion, the design and installation of electrical systems require careful attention to detail and a thorough understanding of the NEC and other relevant codes and standards. By following these guidelines and by working with a qualified electrician, you can help to ensure that your electrical installation is safe, reliable, and compliant with all applicable regulations.